Next topic is about networking. First, because I do not know many of you have already attended some kind of course in university about networking or in secondary school, I will go through crash course of things what is important about networking. Mainly that is TCP/IP protocol, unrelated protocols, ports, TCP and UDP protocols, and how it works in Java. What are most important classes in Java for networking, like URL connection, socket, server socket, and some more details maybe about multiple clients connecting to the same server. Anytime you start learning something about networking, picture like this is shown to attendants, to the students, and what this picture represents. On horizontal axis here, we see two different networked devices which runs some kind of software. And on vertical axis, this picture shows abstraction layers or aggregation layers, how you can look on this communication through the data transmission network. And by the way, when I talk about networks, I mean data transmission networks. I do not mean electricity networks, transport networks, etc. So we talk about things how we can send data from one place to another. And in highest abstraction layer, you can always ignore everything else, and you can talk how one particular software, like application, communicates, or in jargon talks to another application. Like in this highest abstraction level, we can talk how web browser is talking to web server, or mail client is talking to the mail server. And of course, mail is not good example anymore, because more and more services which were provided as a different services with different protocols to the users are eaten up by web and are provided through the web. And what I mean by eating up is something like this. There may be different kind of services which are provided by client and server using different kind of protocols. One protocol, another protocol, another protocol, yet another protocol. But what we have seen for last 20 years is that less and less of these clients are actually installed and used on server, and all these background services are moved behind, like SMTP, like FTP, like some other things, and here everything is through the web, or HTTP or HTTPS. And for example, I still use mail in such way that I have a dedicated mail server, and I'm using mail transfer protocols on my computer. But most of users, of course, connects to their mail servers through the web browser. So that's what means that web is eating everything up. This means many of services which were dedicated services, dedicated protocols, dedicated clients and servers communicating each to other are put behind web server and are provided through the web. So that's about these application layers and protocols. But then what actually is happening is that neither of these applications like web browser and web server are communicating each to other directly. This is abstraction. What actually is happening is that these applications uses different layers of drivers, protocol drivers and then device drivers to send this data to more and more physical management of physical hardware, and sooner or later through these layers where you talk about TCP/IP protocol, about internet protocol, about data link protocol and Ethernet, etc., sooner or later these data are sent to device driver which actually manages some physical hardware like wired or wireless network card. And then in this wired or wireless network card, these data, these bits are represented as signals, and these signals are sent through particular medium to another device. And this particular medium can be just clean air or not so clean air, as Lin cities like for wireless devices, or if these are wired devices, then it's some kind of cable or wire. So what is cable? Cable is wire with 2 or more insulation levels. And so this signal is sent through this medium, either optical fiber, copper, fiber, or whatever, and then this signal is received on the other end of this network. Then the signal is decoded back into bits, and these bits are sent to higher and higher abstraction layer until this particular application like web server receives these data and handles them. And then again it sends something back. You can say and do this abstraction and say that the server is communicating with the client, but actually what is sending these data are handled in very different ways than physical hardware sends some physical signal through the medium, then signal is encoded back to the data and sent back. And computer scientists have split all these abstraction layers into 7 layers, but for practitioners you don't need so many, you usually need only 4. So particularly when we talk about physical network and data link network, we talk about Ethernet as one of leading implementations of networking. Then network transport and session layer is actually TCP/IP network, and then presentation application layer is up to particular application. And if you look on this abstraction in more practical terms, then when this web browser is sending some data to the web server like request get index.html file from this web server, then it contains few bits here, few bytes as this request is sent. So you can say that web browser is sending get index.html to the web server. What actually happens is that web browser sends this data to the TCP/IP drivers of operating system. An operating system adds some header for this data, namely session-oriented data about this particular connection or session, how exactly this web browser was connecting to the web server. This is number of sent packets, number of received packets, something about buffering options, etc., etc. And then this data have another header added before that, which is mostly Internet Protocol source address, destination address, source port, destination port, to this request. And then it is actually sent, in this case, let's say through the Ethernet network. Then again, some other header is added before that, and particularly for Ethernet, that means source MAC address, target MAC address, length of all these bytes after this header, and it's sent through the wired network. And how does it look practically? You can check it and visualize practically using application called Wireshark, which is network analyzer. And yeah, by the way, when we talk about Ethernet protocol, if we look from theoretical perspective, there are actually family of related networks which work like Ethernet. That is Ethernet, Wi-Fi, USB and Bluetooth. And what is similar and what is different between them? Let's say USB, Wi-Fi and Bluetooth. And of course, if you think that Apple only breaks standards like a little bit, you can also add here Thunderbird or whatever, Thunderbolt. What was this protocol called? Blah blah blah. And Firewire. I don't know so much about these protocols because I don't have Apple device to experiment with this. So what is similarities between them? Each of these protocols, each device has unique ID address. In general, it's called medium access control address or MAC address. And these MAC addresses are globally unique. Each of these device vendors who manufacture these devices, they have their own range of these addresses given to them. And then they start with their own window of these addresses and just increment these addresses one by one for each particular device. So that is first important thing. Second important thing is common channel. For example, if it's Wi-Fi channel, you can even go into settings of your router and say use this channel or that channel, or choose automatically that channel which has less other noise inside it. So it means that you can show it in two different ways, but if you have many devices, then inside this cloud all these devices are listening everything what is inside this particular channel. So if somebody is transmitting, everybody can receive that. And third is collision handling. What does it mean? That it means that if all these devices are connected to the same channel and one is talking, all other devices should be listening. If more than one device is talking, it's called collision. Then you can get garbled signals, and then they stop their sending, wait for some time and try to retransmit again. And only difference is following, that USB and Ethernet are wired, and particularly for Ethernet they can create also separate channels. For example, that's how hub is different from switch. So for hub you have only one shared channel for all these devices, but for switch it depends how smart your switch is, but usually it can create as many channels as you have many pairs of devices, that each of particular device through the switch can actually talk inside its own separate channel. So this means several concurrent communications can go in concurrency in parallel through the same device. And these ones, of course, are wireless. But theory behind it, and because these are wireless, they have a little bit more tricky data sending algorithms, because for wired devices, signal do not decay very quickly. So almost 99 point blah 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 % of signal which was sent is received on receiving devices. For wireless devices, most of signal just goes into empty space to the aliens, but some of part of the signal, of course, is received, and so they have a little bit more complexities. For example, how they deal with quality of signal, how do they deal with collisions, etc. But besides that, all these networks are actually in theory the same. They just use different kind of cables or wires to wire them, and different kind of carrying. For example, for these wireless devices, you always have this carrying signal, which is high frequency signal, approximately 2 to, I do not know, 4 gigahertz. And then it is somehow modulated, usually by frequency, to carry actually these bits of zeros and ones. And of course they have different kind of error correction, etc., etc. But otherwise, in theory, all these are very similar. And because these are very similar, when you open this Wireshark, you shouldn't be surprised that it allows you to capture sent packets or frames through the Ethernet network, through the wireless network, and also through the USB device. There is USB and Bluetooth. So if I use wired networks, that would be this one, and I can start capturing. And what I see here, so these packets of information which are sent through the Ethernet protocol are called frames. And what is important here is that these packets are always limited in their total length. Particularly for Ethernet, it is 1500 bytes in total, including everything. And when you look inside this frame, what do you see? What particular Ethernet card or interface was used? And here you see this header. So here I am selecting one particular Ethernet frame captured, and here I can look all this binary, sometimes text-oriented data as aggregated in different ways. And first aggregation is to look about Ethernet. And one important part for Ethernet is this, that source medium access control address is following, and it's usually shown in hexadecimal, delimited by colons. And for older Ethernet cards it is 64 bits in total. 64 divided by 8 is how many? I think 6 bytes. For newer devices it may be 64 bits or 8 bytes. And then it may do broadcasting, so broadcasting would be FFFF to everything. And then that it about this green part for dark green part for here. So source MAC address, destination MAC address, and then everything else is just data or payload. But we can look on this payload again in more details. We can look here on Internet Protocol. Internet Protocol also has source address and destination address, but it also has source port and target port. These are additional numbers here. And if you can look on these addresses, like address for your building, and ports are something like flat number in this building which has many flats. So this is another number in total length in 16 bits. This means approximately 65,000 of different numbers. And then you look on actual data, and this looks like binary data. You don't see much of text here because this is data sent through my Zoom session. But if I, for example, filter it out, just to one particular address, I don't remember how do we filter it out. And then, for example, I open this page. I think this is apparatus, as far as I remember. Let's do it again. Now we have something. So here we see something related to the web particularly. And we may see something also in a text, but of course I'm using HTTPS protocol, so it's still after initial handshake or initial connection is still encrypted. So that's about these payloads and different data structures inside this same data. Now about Internet Protocol and Internet. So you should know already that Internet is a network made out of many other networks, and these many other networks are like local area networks, usually Ethernet networks, which are connected together making Internet. And how does it work? It works in following way, that for each particular device which is connected to the Internet, it actually has its own IP address. And if we draw everything together, so here is my computer, here I have, let's say, Wi-Fi and wireless card, or Wi-Fi and wired. And these are actual devices in my computer. So block means hardware. And I run some software inside it, let's say operating system. So this is software. And each of these devices has if these are Ethernet-like devices and both these are Ethernet-like devices, they have their MAC address. And let's say this has MAC address AABB, and this has a MAC address, let's say CCDD. In practice, this will look like following. This is MAC address for wired network, and this is MAC address for wireless network. And then these devices can send Ethernet frames, for example, from MAC address AABB to something, and it will be sent only so far as you have direct connection to this other device. If this is wired network, only where your cables are connected to these devices. If it is Wi-Fi network, only as far as in this particular Wi-Fi channel this signal is detectable. If it's just can't compete with noise, then of course it becomes too weak and you cannot connect to this particular channel. So you send these Ethernet frames from one place to another. But if you use Internet Protocol, you also have Internet address, and this is assigned programmatically. And for Internet Protocol, you have two different set of addresses, local and global. Local addresses were initially intended only for local reachability for local area networks, and they start with either 10 dot something, (192, 168 something, 172 and something else. So these are local addresses which were intended that they do not go through devices called routers, but if you have many devices connected together, each of them have MAC addresses, each of them have Internet Protocol addresses, and there is a protocol called Address Resolution Protocol, or ARP, which shows, and you can ask for some server, for example, I don't know, and it says that MAC address for this IP address is following. So, and this protocol is used to establish link between Ethernet MAC addresses and IP addresses. Usually this is one-to-one relationship. That means one physical device in Ethernet has one IP address, but in general case there may be many IP addresses to the same device, and there may be many MAC addresses to the same IP address. And in my particular case, you see that Internet Protocol address for my computer is like 10.0.0.11. And there are two different versions of Internet Protocol, version 4, which is widely used, and Internet Protocol version 6, not so widely used. For Internet Protocol version 4, IP addresses are shown as 4 octets of decimal number. Each of ranges is from 0 to 255, or 32 bits addresses. For Internet Protocol version 6, address range is 128 bits of addresses and are shown in hexadecimal number. And here would be, for example, Internet Protocol version 4 address FE blah blah blah, and this FE blah 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 is local address for Internet Protocol version 6. And Then there is, if we talk about devices, another interface called localhost. And localhost is interface implemented in software. It doesn't have any relation to the hardware. So it is like a shared buffer between different processes running inside your operating system. And if you have your web browser and web server inside the same physical machine, then you may connect one client to another, not through invocation of this physical hardware, but through the localhost interface. And for Internet Protocol version 4, this address is 127.anything, usually 001, but maybe 011, etc. So everything which starts. And for Internet Protocol version 6, this is many zeros and one at the end, and many leading zeros may be shortened as colon 1 or colon 1. No, just colon 1. And why this is used? Because this device is much faster than these physical devices, and so if you have a process running inside your computer in the same machine, exchange of data through this virtual localhost interface is much faster than for physical devices. And you already, I think, have seen command ping, which sends requests to respond, and if the device is nice and responds, it sends it back. For example, ping localhost. Actually, we can check maximum speed for it with root permissions. So a few seconds, not more than 2. 311,000 packets were received and sent through this localhost interface. If I ping, right, still, okay. If I invoke actual physical device here and I ping as fast as possible doing this, actually it's approximately the same speed. But if I start sending packets through this device to another thing, and first thing here is local router, and address for it is 10.0.0.1, and this is gigabit Ethernet network. You see that speed is much slower now, but if I ping like odo.lv, which is some server somewhere on internet, again also -f to send as fast as possible, and see that only a few hundred of packets were sent. So, and I mentioned this router. What router is? Routers are devices which connect several, mostly Ethernet networks together, but they can also connect Ethernet together with DSL, Ethernet together with SONET or whatever. And what does it checks? If hub and switch checks only Ethernet frames or these Ethernet addresses, and for example hub doesn't check anything, but switch, which we are mostly using at home and offices, they check what is a source and target MAC addresses for these Ethernet frames, and if these are different, this data actually can send through separate channels to make things faster and more concurrent. But if you have router as this device, router also checks what is told here about Internet Protocol addresses, and router do following thing, that Now let's make this picture simpler and talk mostly about IP addresses. So here is my computer, now just one single box, let's say address is 100.11, and then there is router, address 10.0.0.1, and then somewhere here starts internet. So when I send something and somewhere here is address, let's be precise, here is IP address for odo.lv. So when I send ping packet to this odo.lv, what actually happens is that my computer creates Ethernet frame from MAC address, let's say A, MAC address B, let's say MAC address C, Ethernet frame from MAC address A to MAC address B, but inside data it tells something like this: my IP address is 10.0.0.11, target address is 52.58.11.108, and date is something like please respond. And such Ethernet frame is sent to this router, and router checks this IP data of this Ethernet frame, and it sees that it's not locally reachable, so it needs to be forwarded. And it creates another Ethernet frame like MAC address B, let's say MAC address D or maybe even C immediately, with almost the same data here. The source was 10.0.0.1, target was 52.58.11.108. Please respond. Only thing what is important flag, time to live, was decreased by 1. Initially it is something like 64 or 128, and time to live is because for misconfigured networks packets may go into infinite loops, and they do not go into infinite loop because when their time to live is decreased to 0, they are not retransmitted again. So completely new Ethernet frame was created in completely new Ethernet network. So my network was only from here till to here, but here is another network, maybe Ethernet, maybe DSL, maybe LTE or whatever. Completely another structure of data was created with different frames, but this IP data were unchanged except some details like time to live, etc. And then there may be many other routers which does replicate this frame and again and again and again until it actually reaches this Ethernet device with this assigned IP address, and then it is sent back to this higher abstraction layer, like in this case to the operating system, and it sends it back. And so when we say that this packet is going through this to the network to that, actually several copies of this packet are recreated as Ethernet frames or any other physical structured data, because if these are like DSL, LTE or whatever networks, of course how these data are structured are a little bit different. And you can check how many routers are in between your computer and the target computer using command traceroute, which would be tracer-t in Microsoft Windows. And what this command does, it sends this please respond packets to this target address 52.58.11.108, but time to live is not large. Time to live is initially only 1, then it sends another packet with time to live 2, then another packet with time to live 3, and what happens is that if these routers follow standards and are nice, they send back another packet saying something like this: your stupid packet from here to here died here, and my own address is following. And my own address, it means my own IP address, or this logically assigned address. And then you increase this time to live, some other router sends you response, you increase time to live, some other router sends you response, and then if you reach like Amazon Cloud Network, etc., you reach addresses where routers are not nice anymore. They do not respond. And it means with this particular packet to this address you do not get response. And particularly how Amazon works is that finally we got response from here that with time to live 19. Eventually this server odo.lv responded that the packet with time to live 19 died here, and you got this trace. So these are routers which are not nice. Why some routers are not nice? Because abusing echo requests is one of denial of service attacks. You can ask this, please respond just without any need, and then these routers become too busy. And that's how these routers are connecting together entire internet. And now a little bit about the devil called NAT, or network address translation. In older times, for device to be connected to the internet, usually it needed to have at least two different IP addresses, one for local area network and another for wide area network. Like 10.0.0.11 is for local area network connection only. For wide area network it would be something like in the scope of these public addresses, like let's say 51, 52, blah blah blah. But because Internet Protocol version 4 is only 32 bits and it's only 4 billions of addresses or 4 gig addresses, it's not enough for real use in modern network. Computer scientists invented an idea called network address translation. And how does it work? It works in such a way that only some routers in between your computer and internet actually have public address. And some of you have seen what this public address is when you get banned from this tools.odo.lv server. And everything behind them is still local area network addresses, or this local scope addresses, which shouldn't be routed through the router. But they do something like this, that if I send address from 10.0.0.1 port like 30 through to this address 52, 58, 11, 1 blah blah blah, this network address translation says something like this: my public address is 59, 52, 1, 2, target is 52, 58, 11, 108, and port is like, I do not know, 3333, and destination port is, let's say, 80. And from public network perspective, it looks like that all communication goes only through these routers which has public IP addresses. But when this device responds back to this router, it looks into its own scratchpad table and see that what it presented as IP address 51, 52, 1, 2 and port number 33333, another IP packet should be created back to this original address, which is local area network address 10.0.0.1, port number 33, etc. So what they are doing, they are faking these internal network communications and making everything as a public communication only through these devices which actually have assigned public IP address. And of course, because they also need to have fake ports, because behind these routers may be many other devices, and these are only 65,000 in total, sooner or later this network address translation breaks, and you need to reconnect to your internet bank, to the Facebook, or whatever. Fortunately for Internet Protocol version 6, network address translation is not allowed. And for Internet Protocol version 6, you have this same old school approach that, for example, this Odo.lv server works also with Internet Protocol version 6. And some of you may have Internet Protocol version 6 working if you use TET or LMT as your service provider somewhere in Riga. So here it has local scope, Internet Protocol version 6 address, FE80, blah blah blah. So this is for local reachability only. But to send data and receive data using Internet Protocol version 6, its IP address is following. No network address translation, everything is without any machinery here is network address translation. So if your network provider supports Internet Protocol version 6, you can connect to this server using this IP address directly, and it will send it back without any network address translation. So that's about Internet Protocol addresses and routers. Any questions or comments so far? Yeah. So one more thing then before we go into Java about support. Support is like if IP address is your building, then port is like your room or floor. It is just another number in range of 0 till 2024 or 16 bits of addresses, and it's used to distinguish different kind of clients and servers, either connecting or listening, if they share the same IP address. And particularly for servers, they are so-called standardized port numbers for listening servers. For example, HTTP protocol port number 80, HTTPS port number 443, MySQL not so standardized 3306, etc. So clients usually just take a random free port number which is still not used for these concurrent connections, which is larger than 1024, and servers which are listening, if these are well standardized in internet, may use port number which is smaller than 1024. And then about guaranteed data transmission and unguaranteed. So far I told you all basic principles about Internet Protocol, but usually Internet Protocol are called TCP/IP, where /IP is Internet Protocol. What is TCP? TCP is Transmission Control Protocol, which ensures that if you can send some data through the network at all, they will always be sent without any errors. And how can they ensure for that? They first count how many packets were sent, how many packets were received, they check for errors. If something was not acknowledged as received, this packet is retransmitted automatically, and before any sending of data they do so-called handshake. What is handshake? Handshake is exchange of packets to ensure that the network works. If you have lifeline of client and lifeline of server, and time goes in this direction in this case, client sends one particular packet where important part of it is so-called synchronized flag, which means start connection. And of course everything what I told you here applies. It actually sends Ethernet frame from its MAC address to the MAC address of server if it's reachable in the same local area network, or it goes through the network through the routers, which sends many Ethernet frames but IP address of client and IP address of server doesn't change if you do not use network address translation, of course. So it sends this packet and everything is quite complicated here, and therefore it takes time. You can never send it immediately. And then server sends response back. Important part of this packet is synchronize and acknowledgement flags. And then client sends acknowledgement of this acknowledgement, and here it actually can have payload or some data, and here it is actual response to the payload. So bad thing about TCP/IP protocol is that to check that the network actually works, it has one roundup of interaction between client and server to check that the connection works. And if you have different kind of so this is how most of these protocols where reliability is important works. So first you check that transmission forward and backward works, and then you start interchanging data between them as many times as you need. Bad thing is that, for example, there are many protocols where there is single request, single answer, like ARP protocol, address resolution protocol. Please say me what is MAC address for this IP address, or RARP. Please say me what is IP address for this MAC address, or DNS, which says please say what is IP address for this domain name like kodo.lv. So each of these is just one single request, one single response, and if that would be done with TCP connection, it would take us twice as much time as without confirmation and checking, because for UDP you can just send request, and if you are lucky you get response, one forward, one backward. So for such simple protocols, one request, one response, they do not count and do not ensure that data were reliably sent, because if something doesn't work, it's actually easier to retransmit it again. Then it will be either twice as good as TCP/IP protocol or as bad as TCP/IP protocol if it needs to be retransmitted. Another set of protocols are real-time. For example, when you are listening to this Zoom session or you are watching some live video from Olympic Games or whatever, and you get this stream of data, if you get some glitch in network in real time, there is no any benefit to transmit this data when network works again. So you just drop these packets, you see some cracks in sound, you see some glitches in your video, but it just continues. And therefore, for the small protocols, request response like DNS, DHCP, ARP, RARP, SNMP, voice over IP, which is real-time protocol, you just send packets and receive them without confirmation. Other important part for without confirmation means that, for example, you look on your Olympic Games and there is one poor server somewhere in Japan which provides this stream of data, and here are billions of users who want to see it. If that would be TCP/IP connection, all these billions of users would need to create their own TCP/IP connection with all these memory overheads in this poor server to provide these data reliably. But if you do not use TCP/IP connection but UDP connection without confirmation, what actually happens is that here, until these billions of users, there are thousands or millions of routers which may do broadcasting. And this poor server may say, I'm broadcasting it to everybody, IP address 000. Actually, they do not do real broadcasting, but they say that MAC address is like first router with MAC address, let's say, ABCD. So, and then these routers, if they are good, they do so-called broadcasting, means you broadcast to entire world. And broadcasting usually is used only for local area networks when you say it for everybody who is listening to this particular segment of network. But when you do something like live streaming for games, you do so-called multicasting, which is in between unicast or single communication between one and another and broadcast, which means something like this. And in these routers, they check how many subscribers they have in these subnetworks when they need to resend this data. And they also subscribe to other routers, and this single server can just create one stream of packets for the data, and these routers, which see that they need to retransmit these UDP data streams to everybody else, they just multiply this as a tree of streams till to all of these billions of viewers here. And because you don't need to confirm, you just send to them. And that means that even those here are maybe billions of viewers, this server actually provides just single stream of data to the closest router to the internet, and everything else is then gradually duplicated for as many data streams as they are needed. And because there are many routers, there is no problem with one single bottleneck in this thing. Because everything doesn't work very nicely for multicasts, usually this server still need to provide like many hundreds or many thousands of such streams. But anyway, thousands of streams is still thousands of times smaller than billions of connections through these many clients listening to it. So, even though UDP is not reliable, one important part for it is that latency is lower and it's distributable, that you can just send like a multiplier between these routers in theory. In practice, not every router supports multicasting to this data to not have so many overheads to send the same data to many clients individually. And for everything else, when latency is not so important but reliability of sending data is important, you use these TCP/IP connections, where you count how many packets are sent, you check for connection stability, you resend it, and then you use TCP protocol. So, any questions or comments so far? I take that as a no. So how it's working in Java? Java has built-in support for Internet Protocol. So you can use Internet Protocol as a TCP connections or UDP connections in Java without any other imports from libraries, frameworks or whatever. And in most of cases, when you need reliability, you don't care so much about distributability and scalability. You use TCP protocol, and that's what you will be also using in your practical exercise. But you need to remember that this approach doesn't fit any use case. If you need fast, low latency, scalable solution to send the data, UDP protocol still may be viable to you. And Java doesn't have built-in support for Ethernet. If you need to, for example, do auto discovery of connected devices to the channel or whatever, then you still need to use third-party libraries. And what exactly you can use? If you just need to read some data from some remote website, you can use class called URL from Uniform Resource Locator. And how do you locate resources like http://odo.lv/ or FTP I think is not supported anymore. This is another thing how HTTP or web is eating other protocols like FTP, because what was FTP Odo LV in old times now is HTTPS Odo.lv FTP. So this is yet another case how HTTP eaten up file transfer protocol. Folder is still there, but as a transport protocol only HTTPS can be used. And for this URL you can actually read from many different resources. You can, depending what you mention as a transport protocol in URL. So first tilde the column means what protocol to use. You can read it using either HTTP protocol, HTTPS, FTP, file and jar. And file and jar are locally reachable protocols. You can refer and read something from file in file system or from jar file or jar archive inside jar archive. And such URL class can be used quite widely for auto configuration of your application, something like read first from local file or jar file and then get some updates from remote repository, remote website for more detailed or updated instructions. So what do? You create a URL connection to it and then you open to this URL connection or connect to it, and then you create sockets to read data from them. And what are sockets? Sockets also work on TCP IP protocol, and socket is virtual pipe through which you can read or write. So in previous exercise we get separated reader and writer, and we had to create separate streams, for example, to read something in and to write something out. But socket is abstraction like a bidirectional pipe to which you can assign either reader if you want to read or writer if you want to write. And this socket can be established as a transmission control protocol or universal datagram protocol, just simple IP packets. In most of cases, of course, you use transmission control protocol. So you create this connection and then you create this socket to which you can assign these readers and writers. And of course, if you need interaction, like interact in one direction and other, then you establish both readers and writers. And here is like a communication diagram showing how this server and client works. So servers are always happy to serve, and they are listening on particular port number on many or one particular IP address. And that means when you send packet where target is this address and target port is that port number, then this packet will be given to this listening server by operating system. And then, particularly in Java, how it's made, you create server socket object with particular port number, and you may also say on which particular IP address. If you do not mention IP address, it listens on every possible IP address to this computer. And then it tries to execute accept method for this server socket object. And if nothing happens, if nobody has connected to it, then execution is halted or blocked on this method and nothing happens. Then this process, execution of this process actually goes to sleep, and it is put somewhere in corner of virtual memory, so nothing happens. But then if you create a client which connects to this port number and this host address, and you create this object using constructor. You say create socket on this particular host name or IP address on this port number. Then it tries to connect, and this accept method is executed. So operating system wakes up this process, says, oh, now you can continue this execution of these procedures or steps, whatever you call it, statements. And then when this method is executed, it also returns socket object back. And this socket object and that socket object is absolutely the same. So for client, you create it explicitly using constructor. But for server side, you get reference to the socket object indirectly using accept method. And then you can create, this socket object allows you to use input and output streams. And you can create readers and writers on these streams, and you can aggregate this data whatever you like a characters, like a stream of bytes, like objects or whatever. And then you can read-write through these network sockets in its input-output streams. And then you need to close these sockets either from client or from server. Again, closing socket is very important, because when you create this socket, remember that even though it says a TCP or ODP on server side, it needs to remember several things like client IP address, client port number, sent packets, received packets, etc. So there are some metadata about this connection. And if client just dies and do not use this socket anymore, this metadata about this particular socket, about this particular connection, are stored on server side for some time. How much time? It depends on timeout. It usually is at least many seconds, maybe a few minutes, in some cases even a few hours. And if you just connect and never say disconnect, then the server needs to store more and more metadata about this particular connection, and this is another denial of service attack. But if you close connection, what is happening is that when it sends this packet here, it adds another flag here which says it's final packet from me. And then server knows that this may be closed. Server usually also sends response, this is final packet from me. But in most of cases this is not received anymore, because when this packet is sent, then client is stopped. So there is no listening process to this packet anymore. But it is still sent, even in most of cases it will not be received, because for some reason client may send this final packet by error or whatever, and then if this was sent by error or server misunderstood something or whatever, then this client is stopped by receiving this packet. Or again, it may send another packet here if it was still running, which will not be received by server anymore, because these data structures to consider this particular connection with these port numbers, with these sent packets, are live anymore. But in most of cases it works in the following ways: that either client or server sends this is final packet from me, and other end also sends, okay, thank you, this is final packet from me, which is not received anymore, so it is just dropped and not handled. So I told you about connection types, and yeah, now about buffering. When you use networking, you also need to use buffered reading writing. For example, in this socket, which allows you input-output stream, which is just a stream of bytes. You can aggregate them as characters, objects, whatever. But because it's just a stream, you can also do unbuffered reading and writing. What means, let's say, about buffered and unbuffered writing? Unbuffered writing would be something like sending through the network just 1 byte. And you think, what's important? You just send 1 byte and maybe receive 1 bit again, back. 1 bit, let's say, where 1 means received, 0 means not received. But you need to remember about management overheads, what you need to do to send using TCP/IP protocol. This 1 byte is just payload for this packet. What you need to add for this packet is what was shown in this picture here. You need to say what is source IP address, what is target IP address, what is source port number, what is target port number. If it is TCP/IP connection, you also need to say what is my number of this packet and what was acknowledged, received packet and other things. And then you need to add these addresses, and then you need to say it inside Ethernet frame with source MAC address, with target MAC address, etc. And that means even though your payload or actual data may be single byte here, like here when you look on actual data, date, where it says, for example, sequence number, blah blah blah, timestamp. So somewhere here at the end we see actual data sent from one party to another. You still have many bytes of information as a meta information to send for this particular packet, and it is quite a lot of bytes. And that means if you do something like this, you actually wrap this 1 single byte in this meta info, which is many bytes, and then this single bit is just payload, but it's also wrapped up or preceded by meta info from the server. And then of course you need to wait for latency time, how big this latency is. And again, for localhost interface, this is fraction of milliseconds or few tenths of nanoseconds. That's good. So if you do it through the localhost interface, 1 single step of this interaction could be taking just fractions of milliseconds, so this means you can do it a few thousand times in a second. If this interaction is through the gigabit Ethernet, through the physical device, you see now that it is now quite many of milliseconds, and this interaction in this case would take approximately, let's say, half a second. That means 1 round trip, send byte, receive byte, send byte, receive byte, would take approximately twice in a second. Half a second for one interaction, half a second for another. If you ping like some server in the internet, milliseconds, it is still few thousands, yeah. Then you see that it is taking now, these are fractions, not actual milliseconds. So still few thousand, but less thousands than here. Then you see here that this interaction takes many tens of milliseconds or considerable fraction of seconds. So you can send, let's say, 100 bytes in such way, maybe a few hundred, maybe less than a few hundred. It depends on this latency time, how much time signal needs to be sent from one end to another end, from another end back to one end. But if you do buffering, your latency will still be the same, fractions of milliseconds for local host, few milliseconds in local area network, many milliseconds in internet. But you can send maximum amount of data and you will still have this metadata using the same round trip. And for old school Ethernet networks, it is approximately 1500 bytes, which is everything together. This means for payload it's approximately 1400 something. But it still will be 1000 times quicker than just sending 1 byte by another. And so when you do buffered reading writing through the network socket, operating system says you what is maximum amount you can send through the network. It is a maximal transmit unit. MTU, where do we see MTU? Here. For example, for localhost interface, maximum transmittable unit is 65,000 bytes. For this network card, maximum transmittable unit is 1500 bytes, and that's it. So these are. So, and for example, if you have optical fiber network to your home office or home, this may be even bigger than 1500. So, therefore, if you use buffered reading writing through this socket, then again you put as much payload of your data in one single packet as possible, depending on this amount what your network is supporting. And then for extra exercise, if you are trying to implement it, there are activities particularly for chat server and chat client. Then you need to know how to do support many clients at once, and you do multi-threaded programming for that. But because we will talk in details about multi-threaded programming only tomorrow, so I will leave it for later. If you will be curious, we may discuss it in more details later. And in short, that's it about crash course about Internet Protocol and data protocols in general. Do you have any questions or comments?